Welcome to the final seminar of Mathematics and High Energy Physics of this year at Physics Latam. Today, we are very happy to have Professor Thomas Dumitrescu. Dumitrescu received a bachelor's degree in Physics and Mathematics from Columbia University in 2008 and a PhD in Physics from Princeton University in 2013 under the supervision of Professor Nathan Saver at the Institute for Advanced Study. Before going to UCLA, he was a 5 years postdoctoral fellow at Harvard University. Professor Dumitrescu has a broad interest in theoretical physics. Her research spans many aspects of quantum field theory, including applications to particle and condensed matter physics, as well as supersymmetry, string theory, and mathematical physics. He is particularly interested in developing new theoretical tools for analyzing strong coupled quantum field theories, which are beyond the reach of conventional perturbation theory. Today, he is going to talk about generalized symmetry in quantum field theory. Once again, we are very happy to have Professor Dumitrescu with us today. Thanks for accepting our invitation. And if you have any question, please raise your hand and I will allow you to mute yourself. Now I leave you with Professor Dumitrescu. Please go ahead.
Okay, thank you very much for the nice introduction. It's a pleasure to be here virtually. And even though we just heard the announcement that this is a part of your seminar series, my task was also to make this understandable to the people that are just finishing up the QFT course. So the goal is to go slowly and to stick with a very elementary example and hopefully go into some detail in the 2 hours. And as I said, if you have questions, please feel free to interrupt. So before we discuss what a generalized symmetry is, I wanted to remind you a little bit of the features of non-generalized or ordinary standard symmetries in a simple context. And so let's talk a little bit about ordinary symmetries. And there are many nice examples that you might have at the back of your mind when you think about that. But one nice example is the O2 model, which in field theory you would typically just think of as the quantum field theory of a single complex scalar field phi. So phi is complex, and I'm always going to be in this talk in 3+1 dimensions, or if you wish, 4 Euclidean dimensions. Many of the things that I say are general, and you can do them in any dimension, but just for simplicity, we're going to stick here. And I'm going to write a Lagrangian for this field, which I'm sure is very familiar to you, which involves a kinetic term for phi and maybe some potential. And I'm going to choose the potential in such a way that it is invariant under phase rotations of phi. In other words, I'm going to pick the standard O2 invariant potential, like this. And even though I write m squared here, we'll very soon let m squared be any real number. So m squared can be real or real, but it could be positive or negative. Now, I already said that I was picking my potential in such a way that there's an invariance under phase rotations of phi, and that leads to a symmetry. It leads to an ordinary phase rotation symmetry, which is a continuous U1 symmetry. So in other words, you can rotate phi by any phase, and this Lagrangian here, because it only contains phi bar phi, is invariant. So this is the kind of prototypical example of internal symmetry in quantum field theory, and my understanding is that you've learned about Noether's theorem. So once you have a Lagrangian with a symmetry like this, there's a machine called Noether's theorem to extract a conserved current. And if you apply this machine to this Lagrangian and this symmetry, then you find that the associated current looks like that. So it's this phi bar d mu phi anti-symmetrized combination. And using the equation of motion, you can show that this current is conserved. And that's true classically, but it's also true in quantum field theory if you interpret this as an operator equation. All right. Very good. So this is the continuous, conventional, ordinary, whatever you want to call it, U1 symmetry of the O2 model. I should maybe make a small comment. The reason this thing is called the O2 model is because it actually has O2 symmetry. And we've already seen the U1 symmetry, but O2 is bigger than U1. The reason there's O2 symmetry is because there's also a discrete charge conjugation symmetry which exchanges phi and phi bar. Right. And so if you combine the U1 symmetry with charge conjugation, which is not quite a direct product, then you get O2. That's a small aside, which will not be so important. Very good. Any questions so far? All right. So one thing which I want to also get out of the way is I will mostly be discussing internal symmetries, like I just did. So this O2 symmetry is a flavor symmetry of this model, if you wish. It doesn't act on space-time coordinates. Of course, this is a Poincare invariant model, so it also has Lorentz symmetry. And just like in the case of the O2 symmetry, the Noether theorem gives you a conserved current. So there's Poincare symmetry. And very importantly, there's a conserved current, which is the stress tensor T mu nu. That is there, and you can do many things with it that you do with other currents, but I'm not going to focus on space-time symmetries. But you should remember that they're there, and you can use them if you want to. Okay. Very good. So this is the model, and there are many things you can do with this model, but one of the simplest things you can ask is, what is the vacuum of this model as a function of the parameters? Before you even start thinking about particles and scattering and Feynman diagrams and all these kind of things, the first thing you have to do is to figure out what the vacuum is. And that depends on this parameter m squared. Okay, so I'm always going to assume, by the way, I hope this was clear, that lambda is positive. So lambda is not really going to be interesting for me, but m squared is going to be interesting. So let's vary m squared over the reals. So here's 0. And the easy situation is the situation when m squared is very large and positive. Right? Because when m squared is very large and positive, this potential has a unique minimum at phi equals 0. Potential then just looks like, so if you wish, the potential just looks like this, has a unique minimum at phi equals 0. And you are in the standard situation where all the symmetries of the problem are unbroken, including the U1 symmetry. And you have a unique vacuum, and in this vacuum there lives the massive phi particle. So the massive here as an excitation on top of this vacuum, you have the massive phi particle. So, and moreover, because the expectation value is 0, it makes sense to talk about the U1 charges of this particle. So in other words, if you compute the integrated charge, the integrated U1 charge on a spatial slice, and you are in a situation where this charge annihilates the vacuum, then it makes sense to ask what is the charge of the excitations and the charge of the particles. And then in this situation, you find that the phi particle carries charge 1. I'll say more about that in a second. So this is the part of the phase diagram in which the U1 symmetry is unbroken. Very good. So this is the simplest situation that one first encounters in quantum field theory. Let's look at the other side. Let's look at the side with negative m squared. I should say that here I'm treating the model classically. I'm pretending I can just vary m squared and analyze the potential classically. In quantum field theory, because of quantum corrections and loop corrections, you have to be a little bit careful because that analysis might not be completely correct everywhere, but it turns out to be correct if you make the mass large enough. So in other words, quantum corrections are important in some region here, possibly, that you might have to worry about. But if you only consider m to be very, very large and positive or very, very large and negative, you can actually show that quantum effects are small. So this is a standard trick that we use to analyze phase diagrams in field theory and statistical mechanics. We just take some deformation parameter and make it very large. Okay. Now what happens when m squared is negative? Well, you now look at this potential and it has the famous kind of double well type form. Now here it's a U1 symmetric double well, right? So it has this kind of structure, but it's also U1 symmetric around its axis. So I'm sure you've seen that potential before. Hopefully you won't need to rely on my artistic skills to think about it. This is about as good as I can do. And in this situation, the expectation value of phi is non-zero. It's some complex number v, which is non-zero. And the exact magnitude of v is set by the mass and the quartic coupling and the potential. That's not so important. What's important is that when the mass is very large, v is also very large. So in this situation, the operator phi, which has U1 charge 1, gets a vacuum expectation value, and that means that the U1 symmetry is spontaneously broken. I remind you that the word spontaneously means that the breaking is not at the level of the equations of motion of the theory, but at the level of the solution, at the level of the vacuum expectation value. So the U1 symmetry is still there, it's just that the ground state doesn't respect it. And this has famous consequences. And the consequences come from the fact that there's not one symmetry breaking vacuum, but in fact a whole degenerate circle of symmetry breaking vacuum, because this V could have any phase that you want, and it would still be a minimum of the potential. And the fact that there's this exactly degenerate circle of vacua leads to the fact that the theory has very light excitations, massless excitations. Because if you take the phase of the vacuum expectation value, let's call it chi, and you make it very slowly varying in space-time, that costs you almost no energy. The reason it costs you almost no energy is when you take the limit where the phase becomes a constant, the vacua are exactly degenerate. So this is the sort of simple intuitive argument why in these kind of situations you get massless particles, and those massless particles are the famous Goldstone bosons or Nambu-Goldstone bosons. So in the phase where we have U1 symmetry breaking, you have massless, exactly massless, Nambu-Goldstone bosons. Sometimes people call them NGBs. And so the theory is what is sometimes in condensed matter physics called gapless, or in particle physicists will just say there's a massless particle. Very good. So this is a prototypical example of spontaneous global symmetry breaking. And because the symmetry we're discussing is continuous, the Goldstone theorem predicts the existence of massless particles. And in this case, it's very easy to see with the naked eye what the massless particle is. It's just this chi particle. Now, if you take this formula, if you take this formula for the phi field at long distances, so the phi field at long distances becomes a constant modulus and then a phase, which is a dynamical field. And if you plug that back into the Lagrangian, then you will see that at long distances, the Lagrangian looks something like this. You get a v squared, and then a second derivative of chi. Chi even is a scalar field, but it's dimensionless because it appears in the exponent here. Right? In fact, it's a 2 pi periodic dimensionless scalar. And v has dimension 1, so when you plug into the kinetic term for the phi field, you see that there's a v squared coming out front, and then you get the kinetic term for chi. So this has the right dimensions. So you see that the long distance description of the theory involves a free massless scalar field, which is the chi field. It also happens to be periodic, which is interesting, but we're not going to focus on that too much. And then there's a kind of coefficient here which knows about the symmetry breaking. Now this formula is not exact. There are corrections. The corrections come from considering Feynman diagrams in which you have external chi particles and then some internal massive phi particles. The radial mode of the phi is a massive particle, and we've dropped it from the theory when we focus on the chi, and then when you integrate out the massive particle using Feynman diagrams like this, you'll generate corrections to this effective action that are suppressed by powers of the massive particle. Okay. So that's a sort of general comment about effective field theory, which you should keep in the back of your mind, but it's not going to be so important in most of what I say, because I'll focus on this leading two derivative piece of the theory, which controls the massless singularities. So this is the Lagrangian. The second thing we can do is we can take this expression for the phi field at long distances in the broken phase, and we can plug it into our formula for the neutral current. We can plug it into this formula for the neutral current. And then you see that something interesting happens, which is that the formula for the current here was a bilinear in the field. But when you plug in this exponential form, this long distance form for phi, it actually becomes linear in the Goldstone boson. So at long distances, the neutral current becomes something like v squared times the derivative of chi. And the reason for that, the reason it becomes linear is because only one of the phi's has a derivative on it, and the other one doesn't. And the one that doesn't produce a chi. So this is a very interesting and general formula, which says that whenever you have a broken symmetry, the corresponding current is linear in the Goldstone boson. And that means in particular that if you act with the current on the vacuum, you create a one Goldstone boson state from the vacuum. That's very different than in the phase in which the U1 symmetry is unbroken. In the unbroken phase, in this phase, the current really is a two-particle operator, and when you act with it on the vacuum, you create a two-particle state. You create a state with two phi particles in it. Here in the broken phase, you create a single particle, which is the Goldstone boson. So this is a very general characteristic of spontaneous symmetry breaking, and the reason I'm reminding you of it in this more familiar O2 example is because we're going to see something similar in for generalized symmetries in a second. Okay. Maybe one small comment I should make, which is also a very general statement about spontaneous symmetry breaking, which is once you learn that the current produces a single Goldstone particle, you learn a valuable lesson about the fate of the charge in the broken phase. Because after all, the charge is the integral of the current over all of space. And the integral over all of space produces a projection of that particle onto a zero momentum. Right? You can think of the integral over all of space as a Fourier transform without an exponential, so it's a zero momentum Fourier transform. And this operator tries to create a zero momentum Goldstone particle. But if you have a massless particle, then taking the momentum of that particle to be exactly zero is not a sensible thing to do. For all sorts of reasons having to do with Lorentz invariance that you understand. And so what if you try to do that, then what you get is a state that doesn't make any sense in the Hilbert space, that is not normalizable in the Hilbert space. It's not a legitimate state in your quantum mechanical system. And that actually means that this operator doesn't exist. So that's an important lesson. Sometimes you see the statement that in the broken phase, Q doesn't annihilate the vacuum, but that's not really sensible. Q doesn't exist, so it doesn't make sense to ask whether or not it annihilates the vacuum. So this too is a very general statement about symmetry breaking. Okay, so I think that's all I wanted to review about this model. There were a couple of important general lessons about Goldstone bosons and symmetry breaking that I wanted to remind you of. And also, I want to illustrate in this very simple example an important general principle, which is a sort of Landau principle. The Landau principle tells you that whenever you have two phases, two regimes of a model, like we have these two regimes here, that can arise by dialing the parameters of the model. And if you find that those two regimes realize the global symmetry in different ways. So in other words, here we had a situation where we had this U1 symmetry and it was spontaneously broken over here and unbroken over here. Whenever you encounter this kind of situation, then you know, without doing any additional work, that this red region over here must contain some phase transition that separates them. These two regimes cannot possibly be continuously connected. And that's the sort of Landau argument for phase transitions. And in the O2 model, you can of course see that with the naked eye, because classically, at least if you dial the mass parameter through zero, there is actually a phase transition at the m equals 0 point. Quantum mechanically, it's more interesting, and then you actually have to solve the model in different dimensions to figure out what's going on. But the principle remains valid. So this is a very powerful idea. It tells you that understanding the different possible realizations of a symmetry gives you a handle on different phases. And this is true in this case for these internal U1 symmetries and their generalizations, but it will also turn out to be true for generalized symmetries. So I'll try to say something about that when we have seen our first example of a generalized symmetry. There's perhaps one small comment that I wanted to make about currents and charges that I can use making this, I can make in this context before we move on to our first gauge theory example. So when in everything I've said so far, and also in many presentations of quantum field theory, the first time you see this described, charges like the Q I was writing are operators on Hilbert space, and you think of them as integrated currents where you integrate the zero component of the current. So in other words, if you have space-time looking like that, then the charge is some kind of integral over a spatial slice, and that acts on the Hilbert space living on that slice. And then you consider things like commutators of charges, where you take maybe a charge, so you can consider commutators of charges and operators. And one way you can think of those commutators is that you sandwich the operator O in between those sheets. The sheets have different orientation. So one comes with a plus sign and one comes with a minus sign. And then this sandwich computes for you the commutator of the charge with the operator. And that's the sort of standard way in which you understand how the charges act on operators. And then, of course, the fact that the operators might be charged means that this formula is something like Q times O. If the operator has charge Q, then big Q commutator with O will give you little q times O. So this is the sort of Lorentzian Hilbert space sandwich picture. But this is a special case of a more general picture, which is very useful, and it becomes more useful when you go to generalized symmetries. That involves replacing Lorentzian spacetime with Euclidean spacetime, and treating space and time on an equal footing. So let me briefly explain that. If you are in Euclidean signature, then all of these dimensions are the same. And there's no distinction between space and time, right? So what you can do, instead of considering integrals of the current over a fixed time slice, is you can consider something more general. You can consider the integral of the current, so in Euclidean, let's say in a Euclidean R4, you can consider a three-dimensional surface. So we call it sigma 3. So this here was supposed to be R3, which is the spatial slice. We're generalizing that to sigma 3, which is some Euclidean codimension 1 oriented 3-manifold inside R4. And once you have that, you can integrate the current over this. How do you integrate a vector over a 3 surface in R4? Well, you have to pick a normal vector. So you have to pick a normal vector, and then you do this kind of integral. The normal component of the current integrated over sigma 3. And this gives you some definition or some notion of a charge associated with this closed hypersurface sigma 3. Why is this useful? It's useful because it's a kind of non-trivial generalization of these sheets. See, these charges, these sheets were defined at constant time slices, and the defining feature of current conservation or charge conservation is that you can move them up and down in time without changing anything, right? That's what it means for the charge to be conserved. In particular, Q commutes with the Hamiltonian, so you can move it up and down in time using the Hamiltonian. These surfaces are very similar, but here there's no preferred notion of time. So you could ask, how is the current conservation encoded, or the charge conservation? And the charge conservation is encoded in the statement that this object, Q of sigma 3, is topological. And by topological, I mean that if you deform or you move sigma 3 without hitting anything important, so you deform sigma 3 and you imagine you don't hit any other operators or fields or things like that, then so if you deform or move sigma 3 around a bit, then Q of sigma 3 is constant. And the way you prove this is using Stokes' theorem or the Gauss theorem, whatever you want to call it, and current conservation, right? Because if you imagine making a small deformation of sigma 3, imagine you give it a little bit of a bulge here, then the difference between sigma 3 and sigma 3 plus this little delta sigma 3 is an integral, let's call it delta Q, which is an integral of the divergence of the current over the kind of cobordism, over the interpolation, the 4-dimensional interpolation that you traverse when you deform sigma 3 to sigma 3 plus delta sigma 3. In other words, when you do the deformation, you sweep out a certain 4 volume. And that 4 volume is what you integrate over in this formula. And the thing you integrate over is the divergence of J because of the divergence theorem, or Stokes theorem if you wish. So because the current is conserved, this is 0. And so you see that current conservation or charge conservation takes on a new and apparently more general or powerful form, which is that these closed 3-dimensional surfaces in Euclidean space are topological operators. And of course, the ordinary charge conservation in this setting is a special case of that, because moving these sheets up and down is a very simple case of a deformation. So the reason this idea is, so in the case where you have a current, of course, this Q of sigma 3 is simply a consequence of having the current. So it's just a way of repackaging what you already knew, if you wish. But it turns out that this way of thinking about charges is very useful in situations where there is no current. So sometimes we have situations where there's no current. The simplest situation where we don't have a current is when the symmetry is discrete. Then there's no Noether theorem and no current. But it turns out that one can still define the analog of these Qs, even in those cases. And then there are even more exotic possibilities. Okay. Any questions so far?
There is a question in the chat. Maybe I can read for you. It
Sure.
says, this Landau argument tell us something about the order of the phase transition?
No, that's a good question. So the Landau argument that I mentioned before, that only tells you that a phase transition has to exist. It does not tell you in general the order of the phase transition. There are 2 parts to the Landau argument, so it's useful to distinguish them. The first part, which is very general and very powerful, says that whenever you have a situation like this, there has to be a phase transition in between. This is a completely rigorous, non-perturbative statement. And you can prove it because of the way in which the symmetries are realized differently in these 2 situations. The intuitive idea behind it is that here in this phase you have Goldstone bosons, in this phase you do not. There's no way to go from one to the other without doing something. So this is a completely rigorous, non-perturbative argument, and it holds in very interesting, strongly coupled examples in which you have absolutely no idea what happens here. Okay? And you cannot solve the theory and find out what happens. Then there's a second layer to the Landau argument, which is that Landau wrote down, some kind of what's usually called the mean field theory description of these phase transitions. And in other words, he wrote down a Lagrangian that more or less looked like that, and generalizations of that for different symmetry breaking pattern. And then mean field theory is the statement that you just treat this Lagrangian classically. Forget about quantum corrections, loop corrections, strong interactions, whatever. You just treat this classically and you see what happens. And if you treat this classically, then you will find, for example, in this example, with the U1 symmetry breaking in the O2 model, you'll always find a second order transition. But that is a conclusion that is not in general valid. It's only a conclusion that's valid in mean field theory, meaning classically. And then you have to ask yourself whether loop corrections might destroy the conclusion. And sometimes they do. Sometimes they do, and they can turn a second order transition into a first order transition, or something even more exotic. Yeah, somebody else has their hand up.
Hello, can you hear me?
Yeah.
Yeah, great. So interesting talk. Thank you, teacher. For me, my question is, for example, you are talking about symmetry breaking, and for example, when you have global broken symmetry, I understand that you tell us that it appears a Nebel-Goldstone boson. But what happens when you have a local symmetry broken?
So by a local symmetry, you mean a gauge symmetry?
Okay, but my question is, appears like some particle?
I'm just clarifying. By a local symmetry, I assume you mean a gauge symmetry. So that's a good question, and it allows me to make an important point. So we're going to talk about gauge theories soon, although probably very simple ones. But it is a very interesting question to ask whether there is an analog story of this for gauge symmetries. And this is a question that people asked in the 60s and 50s and 60s, and there was a lot of confusion about it, and it was cleaned up. And the very important answer to your question is that no, absolutely not. There is no consequences whatsoever of a spontaneously broken gauge symmetry. In other words, there are no Goldstone bosons and nothing like that. And the reason for that is extremely important. The reason for that is that gauge symmetries, even though when you look at them at the level of the Lagrangian and when you manipulate them, they feel like symmetries, they are actually not symmetries in any useful sense. They don't act on anything. Right? When you do things correctly at the end of the day, everything is gauge invariant. You work very hard and very long to figure out how to make everything gauge invariant. And once you make everything gauge invariant, whatever you thought was the gauge symmetry doesn't act on any physical observable. That's the whole point of gauge invariance. So if the gauge symmetry doesn't act on anything physical, then there can also not be anything that detects whether or not it's broken. That's very different here. In this example, there's a field, phi, which is a gauge invariant sensible local operator. It's a perfectly good quantum mechanical observable in the sense of Dirac. You can ask what is its expectation value. And it's a number, like 5. And you can compute that number in different vacua. And you find that the numbers are, first of all, non-zero, and secondly, that they differ by phases in these different vacua. So the symmetry actually does something. It acts on something, and it does something, and then we can distinguish whether or not it's spontaneously broken or not, based on whether this or this is true. In the case of a gauge symmetry, if you ever ask what is the expectation value of an operator that is not gauge invariant, then you're just doing something wrong. At the end of the day, if you do things correctly, you should never ask that question. And because you cannot ask that question, there's also no meaning to symmetry breaking in that case. Now, this might confuse you because you might have learned about the Higgs mechanism. And the Higgs mechanism is some version of symmetry breaking for gauge symmetry. But it's very important that it's only some approximate version of the same idea. It's not literally the same idea. So when you work through all the details, in particular, you're careful about gauge invariance, then you will find that in the case of the Higgs mechanism, there is no sharp consequence of the broken symmetry. In particular, there are no Goldstone bosons. The theory is actually massive. That's one of the ways in which people discovered the Higgs mechanism historically. They were trying to find ways of getting rid of Goldstone bosons. Does that answer your question?
Yeah, sure. Thank you.
Okay, great. Okay, so I've introduced these topological operators here. And now we can, I wanted to say one more thing, and then we can move on to our first example of a gauge theory and our first example of a higher form symmetry. And depending on how much time we have, it might also be our last example. The last thing I wanted to say is that this sandwich picture here that tells you how the charges act on local operators is actually a special case of this surface. The reason is that, roughly speaking, you can close up the sandwich on the sides here. Right? You can make a sort of closed surface like this, and then you get a closed surface that looks like this, with a local operator O at the center. So if you enclose local operators by these codimension 1 hypersurfaces, then you actually learn what the charge of the operator is. You measure the charge of the operator. So you can replace this commutator sandwich picture by this Euclidean wrapping or linking picture, and it's completely equivalent. But it turns out that this picture is a little bit easier to generalize than this picture. Okay. Maybe I will follow up on my answer to the previous question about gauge symmetry in one more way, because it's another useful comment to make. One other important distinction between gauge symmetries and global symmetries, which is very important in practice, is that global symmetries are useful even if they're not exact. So in this model, we had an exact U1 symmetry model. I put it in by hand to begin with. But there are many interesting situations in physics in which we have something that is approximately a symmetry, but not exact. For example, a famous example are the flavor symmetries of QCD, particle physics, the SU2 isospin and the Gell-Mann SU3 symmetry. These are approximate symmetries of the theory that are broken by the quark masses. Or in the standard model, you have baryon number symmetry, and that's also not an exact symmetry, but it's very good. And there's nothing wrong with taking a model that has an exact global symmetry and perturbing it a little bit, breaking the symmetry only slightly. For example, we could take this O2 model and we could add a linear term in phi to the potential with a tiny coefficient. That would be a completely sensible thing to do. And then we break the O2 symmetry by a very small amount and we can study the consequences. And that actually happens quite generically in nature. And there's also some deep sense in which it is supposed to happen in quantum gravity. But with gauge symmetries, you can't do that. You can't ever do that. Gauge symmetries, to the extent that you want to talk about them at all, are 100% exact. You should never break them. If you break them by hand, then you're making a mistake. So that's another important distinction. Okay, so this is my very, very brief review of ordinary global symmetries. And symmetries are great. I've only sort of scratched the surface of what you can do with them very briefly. I've already told you that you can diagnose phase transitions and all sorts of good things. So clearly, it's a good idea to try to use symmetries when you have them and to try to find new symmetries that might help you analyze interesting problems. So it sort of seems obvious that you should try to look for more symmetries. And this is not a new idea. People have been doing that since the early days of quantum field theory. People try to look for new symmetries that can be used to constrain physical systems. The problem is that there are powerful no-go theorems that make this hard. For example, there's the famous Coleman-Mandula theorem. The Coleman-Mandula theorem, roughly speaking, says that if you try to generalize, so let's imagine you try to generalize the current that we discussed in the O2 model, the U1 current, J mu, by adding more indices to the current. So you can do that. For example, maybe you have something with two indices, and that actually exists. That's the stress tensor, the energy momentum tensor. Both of these exist. The stress tensor is symmetric, and both of them are conserved. All right. Now you can say, okay, great, let's keep going. Now you make an object that has three indices, or many indices in general, symmetrized. Well, you can ask, are there quantum field theories that have such currents? And the answer is yes. It's very easy to write down quantum field theories that have such currents, but they're all free. So that's what Coleman and Mandula proved. They proved that any quantum field theory in more than two space-time dimensions that has such currents is necessarily a theory of free particles. So the S matrix is trivial. There's no scattering. There's a kind of intuitive reason for that, which is that if you can think of the conserved charges associated with this current at some internal charge, like the Q charge that I was talking about, the conserved charges associated with T mu nu are the energy and the momentum. And the energy and the momentum are conserved in scattering processes. The total energy and the total momentum are conserved in scattering processes. Now, if you look at these so-called higher spin currents, then the corresponding conserved charges would have to be non-linear polynomials in the momenta of the particles. And they would lead to very funny conservation laws involving sums of squares and cubes of the external particle momenta. And if you impose such conservation laws, they're extremely powerful. They're way over-constrained. So they over-constrain the scattering problem in such a way that that scattering becomes impossible. And that's the rough idea. Okay, so this is out. So this is not an interesting way to generalize symmetries in a way that actually leads to interesting consequences about dynamics. And then there's a second interesting generalization, which kind of emerged slowly over the years, coming from different corners of field theory and string theory and so forth. And these are the so-called higher form symmetries. Higher form symmetries are the simplest example of what people now call generalized symmetries. And as I'll explain maybe in 20 minutes or so, higher form symmetries are interesting symmetries, but they do not act on particles. They act on something, right? I made a whole big point about how global symmetries have to act on something, but they do not act on particles. And they do not act on local operators. They act on something else. And this is the way they evade the Coleman-Mandula problem. The Coleman-Mandula problem was that if you throw in extra symmetries to the scattering problem might become over-constrained, and therefore the S matrix might become trivial. But if you have extra symmetries that don't act on the S matrix at all, then there's no problem. Very good. Now, these higher form symmetries are typically graded by a number. They're sometimes called P-form symmetries. And I'll explain what the P means in a second. But in this terminology, P equals 0, so zero form symmetries are ordinary symmetries. So symmetries like the U1 and the O2 model. Something that has an ordinary conserved J mu. And in principle, you can consider all P, but the case P equals 1 is the case that I'll discuss in the rest of the talk, so-called one-form symmetries. And these are the ones, the reason these arise quite naturally and quite frequently in quantum field theory is that they are naturally, they naturally arise in gauge theories. And we'll see in a second why. So in order to demonstrate this, let's consider by far the simplest gauge theory, 3 + 1 dimensions that you learn about in Field Theory 101, and which I think everybody here hopefully has learned about, if recently, and that's free electromagnetism, sometimes also called free Maxwell theory. So free electromagnetism, free Maxwell theory is a U1 gauge theory built using a field A mu, which is the photon. This is a gauge field. So that means A mu is not by itself well defined. A mu shifts under gauge transformations. And here lambda is some function from space-time, let's say R4, to the gauge group. the gauge invariant field strength is the curl of A. This thing is gauge invariant. And F mu nu, which is anti-symmetric, or this is the anti-symmetric field strength, is what you use to formulate the action or the Lagrangian of Maxwell theory. So this is a free theory. This is the free field theory of photons, of massless photons. I will sometimes switch back and forth between this kind of more standard tensor notation and form notation. You can think of a mu as a differential form. You can think of it as a one form, and then the field strength is a two form, which is obtained by taking the exterior derivative of the one form. So that's something like this. So whenever I write a superscript like that, I mean a p form. This is a one form, this is a two form, etc. Very good. Now, there are two important equations satisfied by F. Let's do classical physics first. Let's forget about quantum mechanics and path integrals. Let's just do classical physics for a second. There are two important equations satisfied by F. The first one is the equation of motion that comes from varying the Lagrangian with respect to A. And that equation of motion looks like this. The divergence of F is 0. Or if you want to write it in terms of forms, you have to use the Hodge star. D star F is 0. But as I'm sure you know, there's a second important equation. This doesn't give you all of Maxwell's equations. It gives you only half of Maxwell's equations. And the other half of Maxwell's equations are encoded in what's called the Bianchi identity. The Bianchi identity is, in components, it's written like this. The total anti-symmetrization of d mu f nu rho is 0. And this is an immediate consequence of the fact that F itself is written as a curl. Right? If you plug that in, then you get the anti-symmetrization of two derivatives, and that's 0. That's the Poincare lemma. But in form notation, this is even more obvious because the Poincare lemma is the statement that d squared is 0. And so if you act on F with d, then that's the same as d squared on A, and that's 0. So the Bianchi identity gives you the other half of Maxwell's equations. Very good. And there's one last thing that I wanted to explain before maybe we take a short break. And the last thing I wanted to explain is that, so we're all familiar with the idea of coupling Maxwell theory to electric charge, and we'll discuss that in a little bit. But one thing I wanted to mention, and if we have time, we'll discuss it later in the context of higher form symmetries as well, is that the fact that this is a U1 gauge theory also allows you to introduce magnetic charge. And that's related to the fact that the magnetic field in Maxwell theory can have fluxes. So if you consider a sphere and you integrate the magnetic field, the normal component of the magnetic field over that sphere, that can actually be non-zero. So this is something that was understood by Dirac and then later by other people in different, more sophisticated ways, that the fact that A is a U1 gauge field, in other words, the fact that the gauge parameter lambda here, is circle valued, allows you to consider field configurations on the sphere that carry non-trivial flux. And if you normalize the gauge field in a sort of standard way, then the flux quantization condition can be written in terms of F like this. 1 over 2 pi times F is an integer. And that's the magnetic flux on the sphere. Now, what Dirac famously showed is that in order to describe this sphere with flux on it, you have to cover the sphere with patches, and you have to consider a Dirac string, which is what he did. And then you have to use gauge transformations to argue that either the string is invisible or that the patches can be glued smoothly. And this gluing of the patches is what leads to the quantization condition. Very good. And incidentally, this quantization condition also explains why you can't simply rescale away the gauge coupling. You might think that in this free theory, you can just rescale the gauge coupling, set it to 1, because you can just rescale A or F and get rid of it. But because F has quantized fluxes, that's actually not true. So this is a first example of something kind of very general, which is that when, in field theory and in string theory, we often encounter fields that have quantization conditions or certain compactness conditions on them, and then we see things like that. All right. And the last comment I wanted to make before getting to one-form symmetries, which maybe we'll start after the break, is a comment about electric and magnetic duality. So I'm not going to derive electric magnetic duality for you, but electric magnetic duality is very easy to state. And it was stated about 100 years ago, more than 100 years ago, because it's a property of Maxwell's equations. So electric magnetic duality is the statement that Maxwell's equations, and in fact all of Maxwell theory at the quantum level as well, are invariant under exchanging F and star F. And you can see that at the level of the equations of motion, right? The Bianchi identity is dF equals 0. The equation of motion is d star F equals to 0. So clearly you can exchange F and star F without screwing anything up. And if you think about what that means in components, it's literally just the statement that E and M get exchanged. It's not quite true. There's a sort of subtle minus sign. But in first approximation, it's the statement that E and M get exchanged. So this actually turns out to be an exact symmetry of the quantum theory as well. Free Maxwell theory, as long as you don't couple anything else to it, free Maxwell theory has this duality symmetry. Okay, very good. Any questions before we take our break?
There is some questions in the chat.
You want me to look?
So the first one is, when you refer to mean field theory, is this a mean field over the space or over the time?
Both. Mean field theory in this context means you treat the Lagrangian classically. You just solve the classical equations of motion and you minimize the potential classically to find the ground state. And you ignore loop corrections or any other quantum corrections. So in this setup that I've discussed here, that holds for the space and for the time directions.
Okay, there is another question to say, I have seen some people call broken symmetries as actually hidden symmetries. Can you clarify that, please?
Well, it's a little hard to answer without knowing exactly what you're asking about, because this is an issue of terminology and one needs to get it exactly right. In general, a broken symmetry is just a broken symmetry. And I assume you're talking about a broken global symmetry, because we've already discussed that a broken gauge symmetry is not a symmetry. The only context in which something like what you're asking about arises is there's something called hidden local symmetries in the context of QCD, where people sometimes pretend like there are extra gauge degrees of freedom, for example, in the pion Lagrangian, and there's a sort of technical way to introduce gauge degrees of freedom and basically to rewrite the Lagrangian in a way that looks like it has gauge fields. And when you do that, those gauge fields can be used in some suggestive fashion to motivate various results that people like. But this is a very specific construction that I don't really want to get into the details of. But the important thing is that what is done there is to take a model that has a global symmetry, which is the chiral Lagrangian of QCD, and then one adds some gauge symmetries to it. And this is a perfect illustration of the principle I was advocating before, which is the gauge symmetries are not really a thing. You can have them or you cannot have them. It doesn't really matter. It doesn't change anything physically. Sometimes you need them to describe certain things in a useful way, but there's no sensible way to detect whether or not you have them. You can take a model that doesn't have any gauge symmetries and you can add some extra gauge stuff to it that doesn't change any of the physics. And that's essentially what's being done in those examples. So that's what I would say. The talk, I'm going to give a very simple example of one-form symmetries in Maxwell theory. This is probably the simplest and most explicit examples of one-form symmetries in gauge theories. And you'll see that many of the things I reviewed for you in the case of the O2 model kind of have an analog there. And this is going to be fairly elementary, all of it. We're going to stay in free Maxwell theory, but it's going to give you a kind of sense of why one-form symmetries are useful for characterizing and describing gauge theories. All right, so what are the one-form symmetries in Maxwell theory? Well, let me first try to say what in general a p-form symmetry is. A p-form symmetry, a continuous p-form symmetry, I should say, is something that has a totally anti-symmetric current with p+1 indices. That's conserved. So in this is the way in which is kind of conceptually different from Coleman-Mandula. Coleman-Mandula was about currents that were symmetric on the space-time indices. And p-form symmetries are about currents that are completely anti-symmetric. And that's why they're called form symmetries, because this is a p+1 form, differential form, in the sense of being an anti-symmetric tensor. And you see that what I said before is that p = 0 corresponds to an ordinary conserved current. So that's a special case here, right? So d mu j mu = 0 corresponds to p = 0. And when you set p = 1, you get the statement that you should have some totally anti-symmetric two-form, which just means an anti-symmetric two-form. And now you see sort of with the naked eye why this is something that can arise in Maxwell theory, because in Maxwell theory, we have a field strength, F mu nu, which is anti-symmetric by virtue of its construction. And this field strength satisfies two interesting equations. One is the Maxwell equation. That's obviously of this type. So you see that you already get one example of an conserved anti-symmetric current just from the Maxwell equation itself. And indeed, the field strength F is our first example of a two-form current that gives rise to a one-form symmetry. In this case, it's called the electric one-form symmetry of Maxwell theory. And the corresponding current, let me call it J electric, is basically F mu nu. It's F mu nu, if you normalize it correctly, there's also a factor of 1/e² there. I can say a word or two about where that comes from. So that's Maxwell's equation. And then there is another equation involving an anti-symmetric tensor, and that's the Bianchi identity. Now, the Bianchi identity doesn't obviously look like this, because it's usually written in this way. But then you can define the Hodge dual of F, or the magnetic dual, if you wish, F tilde, In components, it would be something like epsilon mu nu rho lambda, f rho lambda. And in terms of f tilde, the Bianchi identity simply becomes the statement that the divergence of f tilde is 0. So you see that you have a second conserved two-form current. This is now the so-called magnetic one-form symmetry. And it's based on a current J mu nu magnetic, which is, well, essentially there's a 1/2 pi, which is related to the flux quantization condition that I discussed before, and then there's an epsilon times f. So you see that just at the virtue of kinematics, if you accept this definition of what a one-form symmetry should be, clearly Maxwell theory has two of them, an electric one and a magnetic one. Now, why are they called electric and magnetic? Well, I mean, one has an F and one has an F tilde. That's true. And they're also exchanged by electric-magnetic duality. But there's a much more lowbrow way of understanding why they're electric and magnetic. And that's because the corresponding integrated charges are literally the electric and magnetic fluxes. So let me explain that. So what I've explained to you so far is the definition of a p-form symmetry in terms of this current. But the current, the job of the current ultimately is to be integrated over something and to give a charge. So the question is, what can we integrate a conserved p+1 form over to get a conserved charge? Well, very generally, in any context, whenever you have a conserved, so a conserved p+1 form is something whose conservation law you can write like that, using the Hodge star. This is the differential form version of this equation. So the statement that the current J is conserved is equivalent to the statement that star of J, which is a D minus P minus 1 form, is closed. And whenever you have a closed differential form of this degree, you can, first of all, integrate it over some D minus P minus 1 surface, like so. And secondly, this integral is going to be topological in the same way that I just argued to you previously that the ordinary charge integral over a 3 surface is topological, because D of this is closed. Conservation means that D of this is closed. And then if you use Stokes' theorem, you can use that statement to show that this is topological as you wiggle the surface. So this is a general statement in any space-time dimension little d. This is the space-time dimension, and this P is the degree of the P-form symmetry. Now let's specialize this formula to the case we're actually in. We're in 4 space-time dimensions, and we're considering a one-form symmetry. And that means that you should integrate, so what's 4 minus 1 minus 1? It's 2. You should integrate these 2 forms over a 2 surface. And if you integrate the electric current over the 2 surface, you will get the following integral, 1 over e squared times star f. And if you integrate the magnetic current over the surface, you'll get the Dirac flux integral over the surface. So this really hits you over the head, because these are objects that are so elementary when you repackage them in terms of more familiar looking quantities that you're going to recognize them immediately. This is nothing but the integral of the normal component of the magnetic field over the surface. I already said that in the context of flux quantization. And this combination is nothing but the integral over the normal component of the electric field over the surface. So these are things you learn about in undergraduate electromagnetism. These are the so-called Gaussian flux integrals.
Thomas, can I ask something?
Yeah.
In this example, we have identified the P-form symmetries from the equations of motion, but one could still set, for instance, the divergence of A mu equal to 0 to fix the gauge. Would that be considered as another symmetry or not?
No, because
So
this is the recurring theme throughout the talk. Everything involving gauge symmetry is not, at the end of the day, relevant for physical quantities. In other words, whether or not you describe Maxwell theory and the gauge that you said, or some other gauge, is completely immaterial. I'm only discussing gauge invariant quantities, and gauge invariant quantities can't possibly know which gauge you picked. So whether or not you fix that gauge can't mean that you get a new symmetry.
Sure, got it. Thanks.
Right, but that's a good question. These questions are good and important. They're not trivial. You know, people were confused about them for decades. So it took a very long time to kind of sort this out. Okay, so this is so you see we started with something that looked very new and very unfamiliar, and now we've whittled it down to something that is familiar and very simple. So in Maxwell theory, we consider the integrals of these Gaussian flux integrals over closed surfaces, and because the Maxwell equations include the equations div E equals 0 and div B equals 0 if you wish, and their covariantizations, these Gaussian flux integrals are invariant under deformations. And the reason they are invariant under deformations is because we don't have any right-hand side on these equations. We don't have any electric or magnetic charges in the Maxwell equations. If we had electric and magnetic charges, they would sit on the right-hand side of these equations, and then the integrals would no longer be topological. So what you learned from this already is that generically, adding charged matter, either electric or magnetic, breaks the one-form symmetries. And that's what happens typically in more interesting interacting theories. In interesting interacting theories, say like QED, you always add some charged matter, and then some of the one-form symmetry will have to be broken. Often it's broken completely. So there are many interesting theories in physics that don't have any one-form symmetries, like QCD, for example. But there are sometimes cases where a small part of it survives. So then you can use it, and it's interesting. All right. So these are the conserved charges of the one-form symmetries, and these are these Gaussian fluxes. But if you wish, you know, so we've now kind of like completed half of the picture of what a one-form symmetry is supposed to be. What I've given you is an analog of what the conserved currents are, and how once you have the currents, you can build charges. The second ingredient we had in the O2 model is that we actually had a charged operator. We had a field phi, which was the basic field of the O2 model, that was charged under the current. In fact, that in the O2 model, that's how we started the discussion. We said we had a field phi, it was charged, and then we used Noether's theorem to derive the currents. Here I did it the other way around. I just wrote down the currents because they were obviously conserved by the naked eye. But I haven't actually told you what the conserved charges are supposed to be. And this is where we get into an interesting point, which I think will hopefully already also answer a question that somebody asked me in the chat, which is what could these symmetries possibly act on? The thing that I want to draw your attention to, I was excited to get these Gaussian flux integrals, but the thing I want to draw your attention to is that the Gaussian flux integrals are integrals over two-dimensional surfaces, right? Because we're integrating here a two-form over sigma 2. When we discussed ordinary local operators charged under the standard U1 symmetry of the O2 model, we had a local operator sitting here, and we had a three-dimensional surface that we integrated over. We integrated J perp, or star J if you wish, over this sigma 3 to get the conserved charge. So in the ordinary U1 case, we needed a one-form current that was integrated over a three-dimensional surface to act on local operators. Now we have a two-dimensional topological charge, so it's clear that it cannot act on local operators. Remember, I'm adopting this dogma, which you have to buy, that the way that these symmetries act on operators is by wrapping them completely, by linking them completely in Euclidean signature. You should think of that as the analog of the commutator in Lorentzian signature. So if you buy this dogma, then you have to find out what kind of object could possibly link or be wrapped by a two-dimensional surface in R4. And those will be the charged operators of the theory. Well, the first thing that you realize is that these surfaces can't possibly link a local operator, right? A two-dimensional surface cannot link a local operator in R4. In R4, if you have a local operator in R4, O, and you have some two-dimensional surface like this, you can always slide it past the operator. So there's no topological sense in which the operator can be inside the surface. The notion of being inside of a surface, it only makes sense for hypersurfaces, for codimension 1 surfaces. So that tells you that these one-form symmetries do not act on local operators. And that is the ingredient that I was mentioning in the context of the Kolmar-Mandula theorem. If they don't act on local operators, they also don't act on particles. And if they don't act on particles, then they don't have anything to do with the S matrix. So they don't act on local operators, but what do they act on? Well, they need to act on something whose dimension is such that it can be linked by. So we need a gadget that can be linked with a Gaussian surface in R4. Okay. And that's not such a difficult question, because you can, if you wish, you can think of R4 as R3 times time. Think of R4 as R3 times time. So R3 times R, where you view the third R as time. And let's imagine you freeze for a moment the moment in time. So you're really considering now a spatial slice, and then you have a sphere, a Gaussian surface in R3. That's the usual setting in which you're familiar with Gaussian surfaces. You do them in space, not in space-time. So this is a Gaussian surface in space, and from elementary electromagnetism, you know what a Gaussian surface links. A Gaussian surface links charge living inside the surface. Normally, you think of them as electric charges. We'll soon discuss magnetic charges as well. So if you're in a fixed time slice in R3, then a Gaussian surface, S2, can link point charges, localized charges inside the surface. Because in R3, an S2 does indeed separate R3 into an inside and an outside. But now we have to remember that there was a time dimension, right? There was a time direction that we suppressed in this picture. And when you put the time dimension back, you have to also promote these point charges, these local points in space, into lines in space-time. You should think of these lines as kind of world lines of particles. So in space-time, the corresponding picture looks like that. You have the Gaussian surface here, but each of these particles is attached to a line, which you can think of as the world line of the charges. Now, the reason I'm putting world line in quotes is because these charges are not actually dynamical charges, right? We're talking about free Maxwell theory, so I haven't introduced any dynamical charges like the electron in QED. I don't have anything like that. Instead, you should think of these as probe charges. So these are external, if you wish, these are external currents that we put into the theory by hand and whose trajectory in space-time we specify. So we do the thing that you usually do in electromagnetism, which is we add to Maxwell's theory some current on the right-hand side, some electric current, but we specify this current. This current is just some classical function. And the classical function we put in is that we say that the current is localized on the world lines of these point particles. So we said that, you write this formula that I'm sure you've seen before, where we have some sum of the different particles, and we put their charge, and then we put their velocity, and then we have to do some sort of integral over their trajectories, over their world lines to get the current. So this is a formula that you sometimes see in electromagnetism textbooks. And what happens? What actually happens to Maxwell theory when we put in such an external current? Right. So here I'm replicating a formula from electromagnetism, but let's actually see what it does in the path integral of Maxwell theory. Well, the way that this current couples to Maxwell theory is in the usual way that currents couple to electromagnetism. So we put in a linear coupling. It looks like A mu times J mu, where J mu is this classical source. J mu is not an operator. So it's literally this function. We just plug it here. What happens when you do that? Well, what happens when you do that is that each of these particle trajectories, right? Each of these particle trajectories that I've written here that are supposed to represent one of these lines, when you plug it into here, it modifies the path integral of Maxwell theory by something which in the action looks like e to the I times q n times the integral of a mu dx mu, or if you wish, the one form a1, along the particle's trajectory, along the nth particle trajectory. So let me call the trajectory ln. ln is a line in spacetime, and we integrate along that line. And qn, so this is literally the result of plugging in our classical currents into the Maxwell action. I've written it as an exponential because remember the action or the Lagrangian sits somewhere in the exponent in the path integral. So we really have e to the I integral of L d4x. And that integral d4x collapses this delta function onto the trajectories. And the fact that it's in the exponent gives you this formula. So this formula is something that you could have in principle produced using essentially only classical physics, but this object has an important role to play. And gauge theory has a name. This is called the Wilson line. This is called the Wilson line of charge Q, E, or Qn, sorry. And a Wilson line is something that requires two pieces of data. It requires a charge, which I've picked here, and it also requires a curve in spacetime, a one-dimensional curve in spacetime, which is the particle world line. So you see that the Wilson line is the gadget, is the kind of gadget in Maxwell theory whose job in life it is to represent or implement the notion of a probe particle, an external probe particle that carries electric charge. All right. And if we stick such a Wilson line in the middle of a Gaussian surface, like I did here, the Gaussian surface will measure the charge of the line. So what we learn from this, let me draw a picture that only has a single Wilson line. If we have a Gaussian surface here, which is my electric Gaussian surface, and we stick a Wilson line of charge Q that pierces, well, it links the surface. I shouldn't say it pierces it. It links the surface in space-time. Well, it links the surface in space-time, so I can't draw it without some kind of intersections, but it really looks like that. And then this Gaussian flux integral simply measures the total charge inside. And if I just have a Wilson line of charge QE, then it picks up QE. So what we learn from this is that the charged things in Maxwell theory that carry charge under the one-form symmetry are the Wilson lines. And Wilson lines are lines. They're extended operators in Maxwell theory. If you've never seen them before, then they might look unfamiliar because you're used to dealing with only local operators and local fields. The Wilson line is a non-local operator because it involves an integral of the gauge field over the curve ln. Ln is a curve in spacetime. It's also called a line operator because it is supported on a one-dimensional. It has support on a line in spacetime. All right. So it's an interesting operator in Maxwell theory, which is non-local and which is supported on lines, and whose job in life it is to represent the trajectories of external probe particles coupling to the Maxwell field. Very good. So I'm going to make a small comment about magnetic lines and 't Hooft lines. So it has to be very small because there are many technical details I want to skip, and then I want to get to the last part of the talk, which is about the realization of the one-form symmetry in Maxwell theory. So these are electric probe lines. They're very familiar once you sort of write them down. You've seen these formulas before in classical electromagnetism. You could ask, how does this work if I replace my probe electric particle as my probe magnetic particles? Remember, I have a magnetic flux symmetry as well. I have a magnetic flux symmetry, which is the integral of B over the Gaussian surface. If I apply this magnetic flux symmetry to my Wilson lines, I get 0 because they don't carry any magnetic charge. You could ask, can I do the same thing? Can I do something like this and get magnetic charge out of it? And the answer is yes, but it's not exactly like this. It's a little bit more complicated. The reason it's not exactly like this is because you can't write in an easy way, and by easy I mean something like this, the probe world line of a magnetic particle. There's something less easy you can do, which turns out to be correct, which defines the magnetic version of a 't Hooft line. So there are also magnetic lines. They're not Wilson lines, they're called 't Hooft lines. But you should really think of them as world lines of Dirac monopoles. What's a Dirac monopole? Remember I told you before that Dirac famously understood that gauge invariance, U1 gauge invariance, allows you to put magnetic flux on a surface. You can get some non-zero magnetic flux on a surface. And imagine you take a little ball in space and you put some number of magnetic flux on it. Let me call this Q magnetic. Then you can do that. A Dirac monopole is what you get when you take the limit in which this little sphere shrinks to 0 size. Right. So if you have a sphere of finite size, then there's no problem. There's a kind of standard way of describing the magnetic field on the sphere. But you can try to take a limit in which you take this sphere to shrink to a point. In other words, you can take the radius of the sphere to 0. That's and then you get a point in space. So this is a point in space that has magnetic charge Qm. And that's a Dirac monopole. So this is a way of kind of regularizing. If you wish, you can think of this as a way as a regularization scheme, a UV cutoff. The radius of the sphere is like a UV cutoff that somehow regularizes the Dirac monopole, and it's a way of building a point-like magnetic particle. And then you can do this at every point along a line, and so you can build up the analog of a Wilson line, but for magnetic particles. And that's called an 't Hooft line. So an 't Hooft line, which is sometimes called H, is characterized by its magnetic charge and also by the line that it lives on. And it's the world line of a Dirac monopole. So somebody asked me in the chat earlier what an 't Hooft line is and how they're different from Wilson lines. This is what they are, and this is how they're different. So superficially, they're very different because the construction looks completely different. But at the end of the day, they produce a very similar result. They produce an operator that lives on a line L in space-time that's supposed to represent the magnetic charge QM moving along this line. And then you can circle this operator with a Gaussian flux integral involving the magnetic field, and you measure QM. So this is the 't Hooft line is the magnetic analog of the Wilson line, and it's the thing that the magnetic one-form symmetry acts on. So now you have two one-form symmetries, electric and magnetic, and you have two sets of lines, which are the charged operators or the charged defects on which these symmetries act. Any questions so far? Okay. So let me reformulate in a useful way the statement that the electric and the magnetic one-form symmetries are conserved. Remember, before I said that it was the statement that you could deform these Gaussian flux surfaces without changing the answer, without changing the charge. But what is it that is actually conserved? Well, the thing that's actually conserved is the flux, is the magnetic flux. Right, and what the one-form symmetries tell you, the conservation of the one-form symmetry tells you, is that flux kind of can flow continuously along an electric or magnetic line, but it cannot end. And this is the thing I want to make a little more precise. So I've drawn these Wilson lines and these 't Hooft lines as infinite extended lines. You can also consider closed versions of them, but it's very important that they have to be either closed or infinite. You cannot draw a finite end to any of these lines. So imagine, for example, that you take a Wilson line, right? The Wilson lines are the slightly easier ones to work with because there's a simple formula for them. Imagine you take a Wilson line along this curve L, but then you just want it to end at some point here. That's not allowed in Maxwell theory. And the usual reason that you hear about for why it's not allowed is because this operator is not gauge invariant. And that's a completely correct reason. So let's check why this happens. Why is this operator not gauge invariant? Let's imagine you have a line here that goes all the way to minus infinity, and then it maybe ends at some point x in space-time. So that means I'm doing this integral over the one form A from minus infinity to x along some path. What happens under a gauge transformation? Under a gauge transformation, A shifts by d lambda, where lambda is the gauge parameter. Lambda is a function. Okay, and when I plug that into here, I can use Stokes' theorem to turn this into a boundary term. And you see that the Wilson line shifts under gauge transformations by something like e to the iqe. And then I get lambda evaluated at the point x. That's the gauge parameter at the point x. I also get lambda at infinity. But in gauge theories, we always do things in such a way that lambda at infinity vanishes. Lambda at infinity is not actually a gauge transformation. So let me drop this boundary term. That's not important here. The important thing is this part. So you see that this endpoint of the Wilson line at the point x actually transforms under gauge transformations. It transforms in exactly the same way as a local field, of charge, electric charge, QE. If you do QED, for example, and you have the electron field, which is a Dirac field, that's a field of charge 1, it would transform exactly like that with QE equals to 1. So this is not a gauge invariant operator in Maxwell's theory. Very good. So this is an operator that's simply not allowed in Maxwell theory. And this is a completely correct argument for why it's not allowed. It's just gauge invariance. But it turns out that there's also a way to argue for the same conclusion that involves the one-form symmetries. And this gives a sort of nice rephrasing of the flux conservation idea. Right? Remember that the flux conservation idea was that if you have a one-form symmetry, then you can integrate the flux over some sphere that links it. And then you can move the sphere around along the line without changing the answer, right? Because the answer was supposed to be topological. So you get some number here, which is QE, the charge of the Wilson line. Now, if the Wilson line could actually end, then you could take this sphere, you could move it like this, and eventually you would be in a region where the sphere doesn't link anything anymore. In other words, this would simply slip off. And since the answer for what you compute with this one-form symmetry is supposed to be invariant under deformations of the sphere, it means you might as well compute the answer all the way over here, where it doesn't link anything. But if it doesn't link anything, the answer has to be 0, because there's nothing inside. So it actually tells you that these symmetries no longer act on anything and are no longer useful in a situation in which the Wilson line can end. So all of this amounts to the statement that one-form symmetries, if you wish, are flux conservation symmetries. And they imply that lines that are charged under them, charged lines, cannot end. So that's a useful reformulation. It also allows me to make a small comment about theories with charges. I won't have much time to say anything about theories with charges, but this criterion immediately tells you that if you add electrically charged particles to your theory, like in QED, then the electric one-form symmetry is gone, right? Because remember, I told you that in QED, the electron field is some Dirac field, psi, in space-time, but it also carries electric charge, QE equals 1, which means that under gauge transformations, psi transforms like this, where lambda is the U1 gauge parameter, the same one that we had here. So that means that in QED, the Wilson line can be made into a gauge invariant operator by sticking here at the endpoint psi bar of x. Because psi and the Wilson line transform in exactly the same way under gauge transformations. Right, this is the way the Wilson line transforms, and this is the way psi transforms. And if you stick psi at the endpoint of the Wilson line, these factors exactly cancel. So this is a gauge invariant operator in QED. In fact, it's the way we describe an electron in QED. It's the correct gauge invariant way to describe an electron in QED. And the fact that this operator is gauge invariant in QED tells you that the electric flux integral that you might try to use to detect the charge of the line can't possibly be topological. Because if it were, you would get the same answer here and here. So this shows you the fact that the Wilson line can end shows you that there is no electric one-form symmetry in QED, and that's actually correct. And in general, one-form symmetries are broken if you add charged matter. They only survive in theories in which the matter content of your theory is sort of non-generic. If you add all possible matter that you could possibly have, the one-form symmetries are always broken. But it turns out that in some theories, you don't add all the matter that you could possibly add. For example, in QED, you add electrically charged particles to the theory. So the electric one-form symmetry is completely broken, but you don't add any magnetically charged particles. So it turns out that in QED, the U1 magnetic is okay. And it turns out still to be a useful symmetry. And there are other examples. If there were no interesting examples, there wouldn't be any reason to talk about it. Okay, so this is this criterion that I wanted to mention to you. And in the last 6-7 minutes of the talk, I wanted to tell you about something that I already kind of prefaced in the context of the O2 model and the U1 symmetry there, which was the notion of spontaneous symmetry breaking. I explained to you that Maxwell theory has these one-form symmetries, and I explained to you that they act on Wilson lines and the 't Hooft lines, but I haven't explained to you whether or not Maxwell theory is a theory in which these symmetries are unbroken or in which they are spontaneously broken. And that's the last thing I wanted to explain. Any questions before we go to this last topic?
I don't see any.
Okay, very good. So let me go there. So, question. In Maxwell theory, are the one-form symmetries broken? And by broken, I mean spontaneously broken, or not? So this is the last question I wanted to address. Because after all, I was trying to convince you a little bit earlier that you can use symmetries, and in particular the question of whether or not they're broken, to distinguish different phases of field theories. And part of the reason why one-form symmetries are interesting is because they also allow you to distinguish different phases, depending on whether or not they're broken or not. But because they naturally arise in gauge theories, and because they naturally act on Wilson lines and 't Hooft lines, they actually tell you about the phases of gauge theory. So they tell you about things like confinement and deconfinement and Higgsing, these kind of things. So that's why that's the main reason they're particularly exciting. So we should be able then to answer the question about whether what happens with these symmetries in this extremely simple case of free Maxwell theory. Okay, so let me give you the very brief intuitive argument for why. So the claim is they are both spontaneously broken. And let me try to give you a quick argument for why that's true, and then if we have a few extra minutes, I'll give you a slightly less quick argument. The quick argument is this. Remember that in the O2 model, in the spontaneously broken phase, I told you that the U1 current, J mu, was some kind of constant times the derivative of the Goldstone boson, at least at leading order at long distances. So and I said that this was a very general feature of spontaneous symmetry breaking. It's essentially a consequence of Goldstone's theorem. Whenever you have a spontaneously broken internal symmetry like this, the current at long distances creates a single particle pole, a single part. That single particle is the Goldstone boson. And if you take this analogy at face value, you immediately deduce that the one-form symmetries in Maxwell theory are broken, because you scroll back up here, maybe I'll write it again in a second. Remember that the electric and the magnetic currents of one-form symmetry, these ones and these ones, are simply proportional to F. They're linear in the field strength F. So let me write that down here. So in Maxwell theory, both J electric and J magnetic are proportional to F with different index contractions, because one involves F and one involves star F. So it kind of involves different Lorentz components. Roughly speaking, one is the electric field and one is the magnetic field, but nevertheless, both are linear in F. Now, if you remember your discussion in field theory of how you quantize the electromagnetic field, there's a whole discussion about, gauge fixing, and then you expand A mu in plane waves, and then the plane waves are multiplied by creation and annihilation operators. And those creation and annihilation operators are sum over polarizations, and those creation and annihilation operators create single photon states of definite momentum and maybe definite helicity if you want to do that, or some definite polarization. So the important thing, I don't want any of the details here. The only thing that I want you to take away from this sketchy formula is that the gauge field, A mu, is linear in the creation and annihilation operators of the photon. These AKs here on the right-hand side are photon creation and destruction operators. So that means that the field strength, F, which is just the derivative of A, is also linear in the creation operators of the photon. So when you act with the field strength from the vacuum, you create a single photon state of some polarization. And the exact polarization depends on how you contract the tensor indices on F mu nu with something. And it turns out that you will create different linear polarizations. The electric and the magnetic currents create different linear polarizations. One creates the electric polarization, one creates the magnetic polarization, if you wish. You can also take combinations of them. So both of these currents create from the vacuum a single photon. And if you take then this analogy seriously between what happened in the O2 model and what happens here, you would conclude that JE and JM on the vacuum give you one photon. And if you take that seriously, you would conclude two things. First of all, both the electric and the magnetic one-form symmetries are spontaneously broken. And moreover, the photon is the Nambu-Goldstone boson, or the spontaneous breaking. And you see that there's something rather miraculous that comes out of this, because unlike the Goldstone boson in the O2 model, which was a scalar, the Goldstone boson here is a photon, which is a spin 1 particle. And the reason why a spin 1 particle can be the Goldstone boson for these symmetries is because these currents have indices. And those indices give you some kind of polarization vector that describes the photon. So this is the quick, intuitive way of arguing that Maxwell theory is a phase of gauge theory in which the one-form symmetries are broken. And in the terminology of phases of gauge theory, one usually says that Maxwell theory is in a so-called Coulomb phase. A Coulomb phase is a phase in which the potential between electric and magnetic charges is just the Coulomb potential with some. And that's something that you probably computed in field theory by considering Feynman diagrams and taking some limit, then showing that you get the Coulomb potential back. And you see here that you can characterize this phase, this Coulomb phase of gauge theory, which is the most familiar and the most basic phase of gauge theory, in an equivalent way by saying that there are these electric and magnetic one-form symmetries that are spontaneously broken. So that's the last thing I want to explain in detail, and then we can have time for questions. But the reason I wanted to end on this spot is because now that you've seen this example, even without going into any technicalities, you might believe me when I say that the notion of one-form symmetries is also useful to characterize other phases of gauge theories, in particular phases in which the symmetry is not spontaneously broken. And there are very interesting other phases that we care about in gauge theories. For example, in the standard model, we care about the Higgs phase of gauge theory because the Higgs field, the standard model Higgs field, Higgs is the electroweak gauge group. We also care about the confining phase of gauge theory because in QCD, the SU3 gauge group is confining. And that's just in particle physics. And in condensed matter physics, we also care about gauge theory phases. And those can be usefully characterized and in a sharp way using one-form symmetries, and in particular, the question of whether or not they are spontaneously broken. So I'm going to stop here, and then we can have time for